Welcome, everyone. There are still some attendees joining, but as they continue to do so, I'd like to welcome you on behalf of the organizing committee to this fifth in a series of seminars focusing on high-resolution radio astronomy, the sharpest view of the radio universe, VLBI, connecting astronomers worldwide. And this is Denise Gabuzza at University College Cork in Ireland. We've been holding these seminars about once every 2 months, and they've been well attended, and we're considering changing this to about once a month. We'll keep you updated as these plans evolve. I want to mention just a few logistics of the webinar. You will be muted throughout the presentation, but you're invited to type in any questions you may have for our speaker through the question and answer facility. You can send in questions both during and after the presentation, but questions will be answered only after the presentation. Please try to write your questions clearly and keep them short. We'll aim to get to as many of your questions as we can, and we apologize in advance if your question is not among those we have time to answer. I would now like to invite Anna Bartkiewicz to introduce today's speaker, Sandra Etoka.
Hello, everyone. Okay, I'm unmuted. Hello, everyone. I'm happy to introduce Sandra Etoka. She is based at the Jodrell Bank Centre for Astrophysics, University of Manchester. Using laser emission from water, methanol, and hydroxyl at centimeter radio wavelengths, Sandra explores star formation and evolved stars. She mostly uses interferometers like Merlin, JBLA, EVN, and also Nancy radio telescope. Her estimation of distances to evolved stars, what we will hear in a minute, requires very long-term observation, even years, and very systematic works. Sandra, good luck. Let's show us your exciting results.
Okay, so I would first like to thank the organizer for giving me the opportunity to present this project, which is been undertaken in collaboration with Dieter Engel, Eric Gérard, and Anita Richards. Before I go into presenting the phase-lag method itself, and followed by a short concrete example, I would like first to introduce the evolved stars and the evolved stars. I'm so sorry, I've lost the evolved stars object themselves, and a few properties I would like to highlight for you for the future understanding of the phase-lag method itself. So the evolved stars, an intermediate mass stars leaving the main sequence will become a red giant, and then it will enter the what we call the asymptotic giant branch phase, which is in short AGB. When the star will cease the core helium burning and enter the double shell burning phase. During that stage of evolution, the mass loss will dramatically increase. For some of these objects, it will reach a value of 10 to the 4th solar masses per year. And when they enter the so-called thermal pulse stage, which lasts barely 10 to the 4th, 10 to the 5th year, and I will have the effect of creating a circumstellar envelope of dust and gas. So in the next few slides, I will try to characterize a bit better this circumstellar envelope. So these evolved stars have a degenerated core, CO core, and for the purpose of this project, I'm only interested in oxygen-rich objects. So here I schematically present you how the star and the circumstellar envelope looks like for these oxygen-rich objects. So you will, after the core, you'll have a convective envelope. Past that, you have the pulsation starts, and that's where the molecule formation starts too. And in the case where you have oxygen-rich objects, you can obviously create oxygen-bearing molecules. So here I show the main centimeter wavelength maser emission that you can find in this envelope, and through which we can study the kinematic in particular of these objects. So closer to the star, you have the SIO maser at 43 gigahertz, and this emission is before the dust formation zone. Around the dust formation and past that, you can find the water maser emission at 22 gigahertz. And further out in this circumstellar envelope is where the ground state OH maser at 1.6 gigahertz can be found. And this layer of OH is produced by interstellar photodissociation of the water by interstellar radiation. So hopefully you probably know some of these objects very well. You've already heard of them, in particular Myra, one of the iconic objects being Myra A OCT, hence the name of this class of object. And these objects, they have the particularity of being the one with their mass loss rate is not so big that you can still see them, and they're still optically thin. And that means that you, in particular, they've been observed for many years, actually centuries, by astronomer amateurs. And one of the so due to pulsation, the optical light is varying, and with periodic in a periodic manner. And as a matter of fact, as I said, because these objects have been observed for many years, there is a very substantial database of their optical light curves in the AAVSO database. So from this kind of data, you can infer their optical period, which is around from 100 days to 500 days. But there is another type of these objects, the one which actually reach those highest mass loss rates, which are called the OHIR objects. And those objects, they have so much dust in the shell that it blocks totally the optical light, and therefore you don't have any optical data. But as their name gives it away, obviously you can guess that they do show some other radiation, in particular from the dust in infrared and OH masers in the ground state. And these allow us to study them. They've been studied copiously in this regime, and we can also retrieve their period and their variability this way. So now I'm going to focus a bit more on this, on the OH layer, which is the one of interest for the study. So this is the outer part. It lies in the outer part of the shell, the 1.6 gigahertz OH maser layer. And these objects actually show three types of transition. The 65-67 here, which is found a bit more inside the OH maser layer. And so these are called the main lines transition. And it also exhibit emission in a 1612 megahertz satellite line. And as though Myras, a substantial amount of the Myras have a strong emission in those lines, they can the main lines. When it comes to the OHR stars, the strongest emission is at 1612 megahertz, the farthest part of this shell. So now I will present a bit more, I will characterize a bit more this OH maser layer. And it's been proven by many studies now that this layer, in particular for the OHIRs, is like a thin spherical shell, which is in a radial uniform expansion. And because of that, that produced this very characteristic double peak spectrum. And actually, it is easy to understand why, and I'll show why. Is because since it's expanding radially, now you can see that, and also because of the fact that the maser emission is a geometrical effect. So for it to be amplified, you need a velocity coherence. And you can see now that the strongest velocity coherence, you're going to have it in front of the well, in the front cap for, to start with, where the line of sight velocity will be the you will probe the radial velocity at its maximum. While if you get to the tangential part of the shell, this you have purely almost purely a radial velocity in that direction. Therefore, the line of sight velocity is going to be very small, and hence your path for the maser will be short, producing this low emission. And then again, when you go back to this, the back cap of your envelope, you got also here again a line of sight velocity, which is the greatest, and there a strong amplification. So that's the reason why you see this typical double peak. Now I've just mentioned, so this envelope is expanding radially and uniformly, and is a thin and is reasonably thin. So because of that, it can be simply represented by this elliptical relation given here, like give you directly a relation between the velocity and the angular diameter you're probing. And you might ask, actually, are you really seeing something like that? And I can say that, yes, you can see that. I mean, in those objects, it's a nice example here where you can see that the thin shell spherical expanding model is actually compliant for this object. So in this diagram, I should mention that the red point are the 60-60-12 maser emission, and the blue point are the 60-67 emission. And you can see that they all probing nicely this elliptical form. But you can see already that there is something that is not properly probed, and this is this region here, and which actually is the one that you really want to constrain as much as possible for multiple reasons. Obviously, for having the best estimate of your angular diameter. So now I will go into the distance determination itself. And I will just recap here. So yes, OHIRs are MIRAs, but they're optically thick, so we know already that. But they also have longer periods. So their period is starting from 1 year to more than 5 years. We have actually some objects that show period up to 6 years now. And they have a very sizable OH maser shell, which typically range from 2,000 to 10,000 AU. And so you might ask why you want to get the distance of those objects. Well, these objects are found throughout the entire galaxy for the component of the galaxy. So if you want to understand and constrain much better the galactic structure, you do want to know where those objects lies, particularly in terms of kinematics of for the kinematic of the galaxy. Not only that, they found in other galaxies, like for instance the LMC, and for the same reason, if you want also to understand the stellar evolution with respect to metallicity, and understand also how this impact the structure, say, of those galaxies, you really want to know where those objects are in the galaxies. And just passing by, those objects are quite for this method. They are very they're perfect for this method because they're quite sizable. So it means like even if you put this object at the galactic center, it will still be an arc second object. And if you put it in the LMC, the typical object, it will still be a 200 mass object. So it's absolutely mappable. So, but then the problem is, as I mentioned, they are optically thick. So it means that there is no optical data. And even though, for instance, Gaia at the moment is producing a tremendous improvement in terms of parallax measurement and distances for the stellar population, that will not help for this type of transition of this type of stellar evolution. So you need to find another way to find this, their distances. So another thing that you could use is for MIRAS, it has been established that there is a nice period luminosity relation. And so if you get the bolometric magnitude, then it can be a powerful tool to actually determine the distance, just a bit like the Cepheid. So, but unfortunately, what's happening is that this relation breaks down when you reach the around 400 days in the period. So that means it is no longer, as you can see, not available, but no longer, the OHRR don't follow this relation properly, so you can't use that method. So another maybe method you could use is the kinematic distances. Well, this has been proven to be fairly imprecise by a factor of 2, as a matter of fact. So you can't use this method either. Another one that you certainly could use, what you think you could use anyway, is the VLBI astrometry. And then, as a matter of fact, this has been successfully performed for nearby objects. But for this method to work, you really need long-lasting compact maser spots. And as I will probably show you later on, it may not be the case all the time that you can get this requirement fulfilled. So now I'm just going to present another method, which is the phase-like distances. So how does it work? So after basically what you want is it's a very simple method. So because you use the properties of the shell to infer the linear diameter along the line of sight. So you the physical diameter of your shell, and you know, so that gives you its physical measurement, and then you know that this physical measurement will be the same as what you see in the plane of the sky, and then the angular diameter will tell you how far this object is. So it's pretty simple. So how we do that? For the linear diameter, you need to basically measure the time travel between the back and the front of your objects. It's just the delay, hence the phase delay. So it will tell you that the light traveled for so many days. Therefore, this linear diameter has to be of such size. And for that to be performed, you need a long-term monitoring, because you need to get the cycles to calculate, to measure this delay in days. And for the angular diameter, you simply have to measure it on the plane of the sky. Therefore, interferometric mapping is how you get it. So how we do it, how modus operandi. So we basically created the light curve of the blue cap and the red cap part of the envelope here. So that's the raw data. This is an example from one of our objects, and here already you can see that there is not so much maybe in the maximum, but in this instance in the minimum, that there is a delay indeed between the two. And what we do is we simply rely on the light curve shape to measure this delay by interpolation, by simply scaling and shifting the integrated Fleet light curve of the blue peak with respect to the red peak by minimizing this function, where A is the amplitude, the A and C are constants, and for A the amplitude and C the mean flux. So if you do that, that's what you get here. And then to match the shape perfectly, we need to shift this red curve of 60 days. So that gives you the full extent, the linear extent of your envelope, which is in this case 10,400 AU. So that's one part, the linear diameter. So, and for the angular diameter, now we need to map. And from what I've told you earlier on, you can understand now that, so here I'm going to present you a synthetic map of what's going to happen. What you want to have a reasonable probe of the velocity, because the velocity is directly related to the angular diameter of your shell. And when you map, going through velocity basically allow you to go through different depths of your shell along the plane of the sky. And that's what you can see. So obviously you will probe different the angular sizes, and obviously the longest one is when you reach those stellar velocity here. So here is a summary of what I've just presented here. And then you can understand that the main issue is obviously we want to characterize this emission as much as possible. But obviously this is the faintest one, and that's where sensitivity will matter a lot. So another thing also, sorry, we want to constrain by doing that is whether we actually see indeed a thin shell and if it's spherical. And this is another example I'm presenting here where you can see that clearly for this object, that's not the case. And here again, the same as earlier on, those little dots are maser components in this case. And you can see that clearly they don't follow that shape. This is not only very thin, there is acceleration, and also you cannot, that would be the model if you were fully, if you were spherical and thin shell, and then you can see that clearly it doesn't match the observation. And the reason why is because this object is actually a prolate object, which also show a bit of acceleration. So by having high resolution, high resolution and high sensitivity mapping, you want to probe that to make sure that if you have any deviation, and then because that will impact on your estimation, obviously, the distance, because now you no longer, the distance you measuring in that direction is no longer the same as this one. So you want to correct at least for that, or at least being aware that this is not the same. So actually this, the proof of concept of this method is been demonstrated quite some time ago in the late 70s, and through monitoring of 12 OHIR objects through 2 years, and they show that indeed you measure this phase delay by doing so. And then later on in the 80s, there's been a systematic exploration with the Dwayne telescope, 2 main studies, the first altogether involving 33 OHIR stars, variable OHIR stars. And but the problem with this is in the second study, though they had 15 objects in common, they could only find agreement only for 5 diameter within 50%. So something perhaps needs to be refined for this method, or to be well, reliable. And one, I'm going to try to highlight one of the reasons why possibly this is not so good of an agreement in this case. So for this object, which is the one I just presented you earlier, that's their light curve, and you can see for the OH light curve, and you can see that it's nicely sampled. You have points everywhere, and so I would say the sampling of this light curve is pretty good. But for this object, which I'm going to present later as a concrete example, you can see now that even though they have points everywhere, it is unfortunately the monitoring just poorly sampled the minimum and the maximum. And there are some cases, even when it's worse, where they, unfortunately the monitoring was such that they, for whichever reason, the maximum has been missed. So you ended up with very few points to actually constrain your curve, right? And another also possible impact is the fact of using analytical sign function, because then you kind of constrain a bit where the minimum and the maximum will be, and it probably also impact on your results. So coming now to our own the project where it is at the moment. So we've been doing the monitoring for those 20 sources with the Nancy radio telescope shown here at a velocity resolution of 0.035 kilometers per second, and we endeavor to get insensitivity for each of these observations of 100 millijansky. And this has been completed now, so we've got all the light curve of all of objects. But we are, and so I show you a couple of them only, obviously, and then so it's one of them where you have this object has just a period of 440 days, and for this kind of for determining the period, we do use analytical sign function, because we're not interested in the shape, but we're interested in when the minimum and the maximum will be. And I show you here example. So that allows you another example for a very long period, which is 1500 days. And that is, we need that in order to extrapolate the next maximum when we request our observation for the mapping. For this project, we've been using Emerlin and JVLA, and the reason why we've been doing that is, hopefully I will try and convince you about that, is that we actually, the intermediate baseline telescope, and interferometer is certainly the way to go for this kind of object. Because we, for the properties of the emission we find in those objects, they're not necessarily all compact. So you want, so we're using Emerlin and the JVLA at the greatest configuration. And we endeavor to get a sensitivity better than 2 millijansky per channel per beam, to probe as much as possible this faint emission here. So in this figure here, I'll just show you roughly some of these objects for which we have either completed the mapping, or they are already existing maps in the literature, and so we could get a first estimate of their distances. And as you can see, they spread throughout the galaxy itself in different regions. So the aim, what we're aiming at with this project is basically, obviously, to get new phase legs, but we want to understand what's the caveat in the method. So in order to do that, we just, and we also wanted some new, explore the distances, find the distances of new objects. So there's 50% of the sample is composed of objects that already been observed in the 80s. And the other 50% is new sources. Obviously, as I mentioned earlier on, finding the angular diameter of your shell is paramount, and therefore we want to improve those angular by diameter. Hence the reason why we do those new mapping, because the former mapping, where all of this former mapping has been done, were done at a rather poor sensitivity. And we want also, obviously, as I mentioned, constrain any asymmetries to make sure that asymmetries in the envelope. And the ultimate game here is to constrain the distance uncertainties of the method that has a limitation, and for instance. So now we'll go through a concrete example, and going through this concrete example, I'm also going to highlight some of the caveats and some of the things we learned throughout the way. So this example is for OH 83.4 in short, and here is the the raw data for the blue and the red peak. And as I mentioned earlier on, the way you do it is simply you shift and you scale and shift, and that gives you this those two light curves. And then you obviously can get, for this specific object, the phase delay is only, or the delay is only of 30 days, and that tells you that the linear diameter of this object is 5,200 AU. So now we've got the physical diameter of this shell. And for this specific object, we used Emerlin down to a resolution of 0.17 kilometer per second. It's a trade-off, so we could get the sensitivity of less than 20 millijonskis, and we managed to reach a 14 millijonski per beam and per channel. And here I present the spectra out of the final data cube for this observation. And what we tend to do to make sure that we want to make sure that we didn't, or at least we want to know if we've lost any emission. So we endeavor to take around the time of the maps, a single dish observation of the object to compare the spectrum and see if we lost any emission there. And then you can see here superimpose the NRT observation that is being taken very close to the Emerlin observation, and you can see that we recovered all the signal. So we're confident that we, down to the sensitivity that we managed to achieve, we got everything. So here is a channel map of this emission of the star. In this specific instance, I actually average 5 channels together to boost even more, so basically increasing by 2 the sensitivity, so that you can to see better what's going on in the inter-peak region. So obviously, because I wanted to highlight this, that saturated the very strong cap emission. But if you actually discard those and do just a moment map zero of this emission, that is, you average all the emission from the channel here from given in that velocity range, that's the representation of the shell that you have, the angular diameter of the shell that you have. And from this, you already know that your angular diameter is 1.8 arcs. It allowed us to infer the angular diameter of this object to be 1.8 arcs second. But so another normally way of, and the way you can probe this velocity versus theta relation is generally by component fitting of the maser. So in this figure, I show you the maser component that is been obtained by doing this individual component fitting on each individual channel. And then what I mean by component is if a maser spot survive for at least 3 consecutive channels, it's turned into one single component. So not all the maser spot, but one component. And then you can see here, and that cycle is basically where we know already from earlier on that this is the full extent of the shell from the faint emission. But you can see here that, okay, you can, it's reasonably compliant with the thin shell model in the sense that you have this strong compact blue and red shifted emission red band at the center. And when you explore the velocity towards the stellar velocity, you explore those more bigger angular resolution. But you already can see that there is no yellow, orange, or even light green. And that's basically what if you use those components, what you retrieve for the the velocity versus theta versus velocity diagram. So yes, the channel map is consistent with the thin shell model, but unfortunately, if you use this method, you can see that you cannot achieve component fitting for a good fraction of the interpeak. And if you were to rely on that to find your angular diameter, it would be very inaccurate. So, okay, you say, okay, if you increase the insensitivity, which I did artificially here for this specific 5 channel average channel map, then I can now do the same exercise, but instead of doing this, I can no longer obviously do this average. So this diagram is now, this figure is now for each individual measure that is found on this very poor resolution, velocity resolution channel. But now by doing that, you can see that sensitivity matters, because now all of a sudden you can see, you explore a bit more this shell, and you can start to see those orange and light green components for measure emission. So you can get some of this, still some of this emission have a bit of a compact component in there. So that allows you to explore a bit more this theta versus velocity diagram. But one thing you can see is now, because you lost, first of all, you lost the velocity resolution. So it constrained it a bit, the constraint in velocity is not as good. And also because you no longer have this filter about the 3 channel, you also pick up all these measure emission that are kind of created by the turbulence and so on, which are not fully compliant with the shell, the overall shell properties. And still, in any case, you ended up not being able to, for this specific object, fit any Gaussian in the very faint part where this is where you want to have this information. And the reason why is, I'll show it here. So that's now I'm going to do the same moment like 0, but only for those very narrow, very few channel around the stellar velocity. And what you can see, what you retrieve is this ring here, which actually is the one that allows you to infer the full extent of your diameter. But as you can see, there is very, very few places where you have actually compact emission. And what's happening is this emission is rather a diffuse measure emission, and the component fitting will fail no matter what. And that's where having intermediary baseline interferometer matters in this case, because if you imagine if you were to go to very high resolution for this kind of mapping, you will simply wash away this emission, and you will be left with the very compact one, which are very close to the center. Don't probe the full extent of your shell. So in this case, intermediate baseline interferometer are really important for this kind of job. So now I'm just going to put up all these things together. So we already know, well, we know now the angular diameter is 1.8 arcsecond. And we know from the monitoring that the linear diameter that we inferred along the line of sight is 5,200 AU. Therefore, because we know that this distance is, this diameter is having such extent on the sky, we know that this object is 3 kiloparsec away from us. And I will just conclude this this talk by giving you the 5 must things that we learn along the way that I think is important for the phase-like distance determination. So in terms of, for the linear diameter determination, I hope I convince you that high cadence and of a spectral, the spectral observation are important. And what I mean by high cadence is, having you sampling really your light curve as uniformly as possible. The best way to measure with the the best accuracy you can possibly get, the lag, the delay between the blue and the red and the blue in light curve, is not to rely on fitting function, but simply on the shape. Because this shape, if you imagine that you just rely on the fact that the conditions are roughly the same throughout the entire envelope, and therefore this shape, as I hope I convince you, is preserved from the back and the front, no matter what. Even if the intensity is not the same, this shape is preserved, and you can use it. It's a very powerful tool to use for measuring this delay. And obviously you want, for multiple reasons, you want to make sure that this light curve coverage is more than 1 year, not only for the period, also, and it will allow you to time perfectly your observation, your mapping observation, because you want to do these ones at the maximum of the light curve where this interpeak emission will be the strongest. For the angular diameter, I hope also that I convince you that the faint tangential emission, which are cotangential, which is on the other side of the shell, is paramount in order to infer the full extent of your shell. And high sensitivity, and so therefore high sensitivity is important, but also like a complete understanding of your shell symmetry or asymmetry is important. And because you want also to constrain that in order to know if you have to correct or if the thin shell model is valid. And I thank you for your attention.
Thank you very much, Sandra. We've got a number of questions that have come in, so we'll start with them now. We have a couple of questions about the question of variability. It seems that some of the scatter in the phase lag light curves can be attributed to variability inherent to the individual maser sources, right? Is it understood what causes those variations of the different OH maser components, and how much does that impact your ability to do the phase lag method?
Okay, so yeah, so each individual maser, they will be, because it's maser emission, so obviously depending where they are, they will amplify the emission more strongly than other place. And then so you will have this variation happening in the light curve. But as I mentioned it at the end, the reason why we actually average over the front and the back part is to kind of actually smooth that. We don't care because, as I just mentioned it earlier on, by doing so, because we assume that the conditions are roughly the same throughout the entire shell, we smooth that out, and then the light curve shape, as I hope I convinced you earlier on, is exactly the same provided that you scale it, is exactly the same from the back and the front, and that's the power of actually using this overall emission as a signature from the front and the back, because now it's that the shape matter. We don't care if there are bumps, so long as they reproduce in both sides. We just actually use them to shift. So in that sense, it's actually helping to have like this kind of characteristic shape, because it allows us to actually align them even better.
Okay, thank you. How often are the variations nicely regular, like some of the ones that you've shown? And are there some cases where there might be, for example, changes in the period with time or drifts in the period with time that might make things more difficult?
Yeah, so actually there are some of these objects which actually, because as you imagine, they are at the end of their life, so they will eventually become planetary nebulae, so they will cease to be variable. And so yes, some of these objects stop, so they start to not have any longer periodicity visible. And then yes, for this kind of object, it will not be possible because you need variation to actually adjust the front and the back of the cap. So yes, not all of these objects are variable. When they reach the end of their life on the AGB, they will virtually cease that pulsation, the response, to the pulsation will disappear. And then the OH maser will not show any more that. And for these objects, you cannot use that method. So you have to rely on the variable ones.
Okay, thank you. Another question, this time about the angular diameter. When you're measuring the angular diameter, do you observe at a specific phase, maybe like the maximum OH or something like that? If that's true, does that mean you can do that only for a few stars for each VLA configuration, for example? And do you observe that diameter more than once to get better sensitivity in combined images?
Yeah, okay, so I explained that at the end. Yes, the reason why we had the monitoring, the NRT monitoring performed before we do the observation is actually because we want to probe as much as possible this faint emission and to have it to get this probe the best. The best is when you're at the maximum. So yes, we do. That's the reason why we do that. So we do indeed the phase matter. We really endeavor to do our observation at the maximum of the light curve, around the maximum, whether on the, but that gives us a reasonably big window of opportunity. You can imagine for long period variable, this can be fairly big anyway. I mean, if you have like a 5-year period object, this is going to be several months before it goes down. And but yes, we do have to pay attention. That's what we're trying to do. That's what I was saying at the end. We are actually using the monitoring to infer when to observe, and if we find any kind of so actually at that the second when we propose the observation, we endeavor to restart the monitoring to make sure that we can indeed maybe it's going to be, oh, sorry. Okay, anyway, it's not the one. So we endeavor to start the monitoring at the NRT to see if our analytical function fit and that we are indeed we're going to be toward the next maximum for this observation. And we propose a certain range for this observation to be observed. And if we think there is something wrong, we just, inform the people that we, of that. But yes, the phase matter here.
Okay, another question. How accurately can you measure the lag and the size?
Okay, so far we have been very conservative and we giving a 20% overall uncertainty of the distances. The lag with the phase, even though we observe those objects every month or 2 months, because we relying on the shape of the light curve, we ended up having, if you move it even by 5 days, you can really see. So it can be very precise just by doing that. And obviously the angular diameter is down to how you measure this faint emission, how deep you can get. And so this can be depending, of course, of your resolution. But that is overall give you for so far with roughly are confident about 20% in the distances altogether if we add all these uncertainties in the angular diameter, which we can constrain in 2 different ways, as I hope I showed you by the phase lag, which is very nicely, it's better, it's more accurate than using any other method. And we have like this proper cadence. So yes, we have altogether, I would say, so far we wouldn't claim more than 20% in a distance, but
Okay, thank you. And what is the maximum distance that the method can be used for? And is it limited by interstellar scattering towards the galactic center?
So, well, yes, I guess right down in the galactic center, you might have indeed scattering, but overall you can rely on, so if that objects, so you will lose obviously a bit of emission, but we have an object at least for 5 kiloparsec, so we are not yet on the other side, so I can not tell how much the scattering will have impact, but we definitely went past the 2 kiloparsec, and actually, if you are not in the galactic center, so if you go towards, say, the LMC, maybe, hopefully, we haven't tried that, but we just think that so long as you have enough emission and you left, you should be able to infer the diameter. Maybe, obviously, it has still to be proven how much the insert element impacts the the uncertainties of the angular diameter. But as far as if you are away from the galactic center, you don't have that effect as much, and fairly confident that it's still going to work reasonably well. I mean, on the other side, I still have to try an object and see if we filter too much of this faint emission and if there aren't enough of this compact. So I cannot exactly confirm how good it's going to work on the other side, but we have some of these objects. So watch this space, and hopefully the next one will be one of them and can give a better estimate. I don't want to give numbers just now.
Okay, thank you very much. It looks like that brings us to the end of our questions. So at this point, I'd like to thank Sandra once again for her very interesting talk, and thank all of you for coming, and especially to those of you who paid attention and asked good questions. We'll keep you up to date when we know when the next of these seminars will be happening. And I think Benito Marcote has an announcement that he'd like to make about the EAS VLBI session.
Yes, so everyone be aware that at the EAS, the European Astronomical Society conference that will happen in a couple of months, there will be a session dedicated in particular to VLBI. So all these topics will cover there, and will be a really great opportunity to share all the scientific projects that are related to VLBI, that basically covers many of them, and to share all the experiences there and see what's the state of the art and how you can run these facilities to use in your science.
Okay, thank you very much, Benito. So thanks again to all of those who came, and we hope to see you again in perhaps another month or two. Bye-bye for now.